The first method that I am going to present is the one presented by Marsden. This was maybe the first stabilization technique proposed to avoid the generality problems. In this method, a modification is introduced in the master problem by adding a new set of primary variables, actually 2 by row, that in the dual problem define boxes around the previous value of the dual variables. So the values that I am signaling here are bounds that are imposed iteratively during the column generation algorithm. Okay. The penalization for these variables in the objective function of the primary problems increase dynamically during the column generation algorithm. So in some moment it is not profitable to include these variables into the model, and the solution reached is the optimal solution. As you could see, this is a relaxation of the original problems that allow to obtain solutions that are not feasible, that actually are not feasible in the primary problem. The second strategy proposed is the one proposed by Dumerle. This is a generalization of Marsden model in which, same as in Marsden model, a set of perturbation terms are included in the original model. However, also are included bounds on the stabilization in the stabilizing terms, such that from the viewpoint of the dual problem, movements are allowed around of the analytical centers, but larger movements are penalized in the objective function of the dual problem. In the same way as Marsden model, at each iteration the boxes are recentered around the dual values obtained in the previous iteration. In this method, we could say that we have defined a 3-piecewise linear penalization. Okay, because this is the real effect in the dual problem. Okay, first we have a region without penalization. However, when the dual values are out of these bounds, a penalization appears that is avoiding the appraisal of larger movements. Other method, and the simplest one, that use the dual values to accelerate the method of convergence is the one proposed by Nim. In their method, Nim had proposed to use a linear combination of the newly obtained duals and the obtained in the previous iterations to obtain new columns at each iteration of the column generation algorithm. By using this method, the auxiliary problem costs are differentiated of the typical column generation algorithm, and he has obtained results that are interesting regarding to the acceleration of the column generation algorithm. As could be expected, some iterations do not allow to obtain reductions in the original problem. However, the method has not reached yet an optimal solution. If this is the case, the next iteration will use the original set of dual values obtained in the previous iteration, and we could say that we have a misprice. Regard to the diversification methods, I have proposed the use of the diversification boundary solution and diversification by selection schemes, but by using heuristic algorithms. First, I propose the use of a mono-objective genetic algorithm to return and select the k-best reduced cost columns. The proposed method uses just the reduced cost criteria to select the columns that must enter into the problem. The second method uses a multi-objective genetic algorithm, a modification of the NSGA2 algorithm, to select the columns that must enter into the problem. As could be observed in the models, the breach is an important criterion because this is the penalization for each variable in the objective function of the model. To use the breach as a criterion to generate columns, allow to enter column that doesn't have the best reduced cost but has a really low breach. But most important, guarantees that columns with a really good reduced cost entry only if they have a low breach. Both genetic algorithms were based on the same structure. First, a chromosome is composed by a set of binary variables A to B that indicate if a sensor is part or not of a sensor subset. The position of each sensor of each variable on the right indicates the sensor that we are talking about. After some experiments conducted, it was observed that a population of dirty chromosomes generated fits our necessities. This is the notation that was used to generate the instance. To evaluate the method, the AA is varied with the number of sensors, typically 50, 100, and 150, and 200. BB represents the number of targets that need to be covered. Typically, we are talking about 30, 60, 90, and 120 targets. By last, CC is related with the sensing range at which each target is considered covered by a sensor. In this slide, I'm presenting the nomenclature that was used to evaluate the different methods' behavior in the real instance. The first thing that you could observe is that the use of stabilization techniques effectively reduces the number of required iterations until reach an optimal solution. This behavior was observed for all instance sizes. Also, it is possible to observe that NIM's methods, although simpler, presents better results than the other stabilization techniques that I am presenting. From the viewpoint of the associated bar problem, it was possible to observe that comparing the optimal solution with actual solution regard to